We're going to be talking about building multi-tenancy machine learning applications with GKE and then using Istio to gain visibility into those applications. And our goal is, as a company, is to really better understand the Earth. So that's what we're going to be talking about for the next 40 minutes. My name is Tim Kelton, and I'm one of the co-founders of a startup called Decart Labs. And we're going to be showing some of the machine learning models that Decart Labs has built for its customers. And just a warning, I guess, we're a very kind of pixel and imagery-focused company. So you're going to see lots of satellite images and lots of aerial imagery. So I hope that's OK, and that'll keep things exciting. Then we're going to talk about how we leverage Google Cloud and the components we use, is specifically Google Kubernetes Engine, and then we gain a lot of visibility by using Istio on top of our microservices. And then finally, for an exciting finale, my colleague and our head of engineering, Sam Skillman, will join me, and we'll show a brief example of running multi-tenancy workloads, machine learning workloads on there. So I hope you come away with some great ideas about running multi-tenancy and how Istio can help give you visibility into your microservices. But I also really hope you come away with some ideas of how better understanding changes that are happening on our Earth every single day might actually impact your businesses or your organizations, and gaining insight into that can really provide those insights. So who here has heard of Decart Labs? A few hands. OK, that's actually kind of awesome. Our story is a little different than the stereotypical Silicon Valley startup. While we do have Silicon Valley VC funding and we do have veteran Silicon Valley leadership, we're actually and we have offices here and in New York. Our headquarters are actually way up in the mountains of Santa Fe, New Mexico. And it's kind of a weird place for a startup in one way, but that's because myself and the rest of the founding team were scientists, researchers, and engineers at Los Alamos National Laboratory. And there we were actually working on machine learning and applying that to a range of real-world problems, including remotely sensing the Earth. And so the cloud, we don't have a data center. We don't even own a single server. So the cloud, we basically couldn't exist without this infrastructure. Yet on any given day, our staff of scientists can build models, and they can build them over petabytes and petabytes of data, and they can scale them on thousands of cores. And that's all basically because of the cloud, and that's really why we're here. So our story is a bit of, in some ways, it's really about sensors, and in some ways we're looking at sensing the Earth. But sensors are really at an inflection point right now. They're changing from a world where data was kind of individually collected or manually entered to one where it's basically being continuously sourced and automatically input by sensors. They're getting better and better resolution. We're seeing better range, better data transmissions of sensors, and the costs are just dramatically decreasing. I mean, this is everything from things I use riding my mountain bike, but all the way up into the satellites and remotely sensing the Earth. Just not that long ago, almost all satellites were basically government funded. So they cost, hundreds of millions of dollars for a project. And now an engineering lab student can make a CubeSat and can launch that up into space. Or they can mount a sensor that they've made in a laboratory to measure things like radio frequency. They can mount that to a drone or fly it around on a plane. So this world is changing, and it's basically becoming a continuous, we've gone from these infrequent samples to almost continuous measurements. And one of the really big core challenges that we've always had with satellites and remote sensing of data is getting access to the data. Sure, you could click and download an image, and it was made for that human interaction and that human analyst. But with machine learning, that really has changed. We can process and look at imagery that humans will never, ever look at in in our lifetimes again, because there's just so much data. And the cloud has been one of the big enablers in the last few years. It was really hard. It's now finally possible to process and have every single piece of satellite imagery or aerial imagery or remotely sensing data and have that available and basically build that and make it machine learning ready. And so this imagery that we've put into our platform is fully global in coverage. And then it crosses many different spectrums of light. Behind me, that's showing near IR on a global composite. And then it's across many different modalities. This is, sure, we have human visible light, but this is something called synthetic aperture radar. It's not where the sun shines off the Earth, bounces off the Earth, and a camera captures it. Instead, the satellite emits a radar signal actually down onto the Earth, bounces that off, and captures it. It's giving us a global height measurement around the whole world. And then it's through time. And often it's this temporal cadence that provides maybe the greatest analytical insight when we're building models. Behind me is NASA's MODIS imagery. This is showing vegetative health. That's that really, really bright green. And this is showing a single frame for every day. So this is looking down everywhere in the US every day. And this is 15 years of imagery that's playing behind you. So you're seeing 500 million pixels in every single frame of that video. And so the visibility and accuracy advantage comes from the ability to combine multiple input sources into the models. There's not really one data set that provides you all the answers to the really consequential problems. And so these are across spatial, spectral, and temporal. And it's this fusion of both internal data sets that we build as a company, but it's also public data sets. We have a lot of stuff, imagery from, say, NASA or European Space Agency, institutions like that. It's commercial data sets. And they all have a critical time and a place context that's really required to produce accurate models. So right here, I would like to just kind of dive deeper into what I'm talking about as an example. This is Des Moines, Iowa. It's kind of do we have anyone from Des Moines? I don't see anyone. Okay, I didn't think so, but you never know. So this is a combination of urban and agricultural landscapes. We're seeing the vector data on the right. This could be ground truth locations, or maybe it's one of our customers' pieces of infrastructure that they've wanted to tag for changes over time. And then we have on the far left, we can show vegetation and vegetative health. And in the middle, you can see that synthetic aperture radar I was talking about earlier. The really bright pink and white is higher height objects. And the challenge is making a range of different sensor outputs from a range of different agencies, like NASA or European Space Agency, make it all uniform and queryable so they can be used as all as inputs for those models. And so our customers and our team of applied research scientists solve a pretty broad range of problems with ML. And so every week we bring new sensors and new data sets in to try and solve those problems. So what are some of those examples of types of models that we've built? To extract the most data, we've built this modeling platform for complex global systems. And now we have around 15 petabytes of data in our archive. And with this full historical time stack, what it does is allow us to go back through time and track both conditions and outcomes so we can generalize that relationship. And then we can use it to make predictions based on today's observations. And then we can track new outcomes, and we can measure accuracy, and we can basically continuously be updating these models. So this is an example. This is showing construction and buildings being started, and that's correlated to steel demand. This is another example showing object detection. We are doing detection on buildings, and we have run this on the entire state of California, as well as numerous other parts of the world. And actually, one of our scientists was just telling me yesterday that last Friday, we were trying to understand things like hurricanes and maybe how hurricanes might impact a state like Florida. And in just a few hours, they were able to scale up and basically map out every single building in the state of Florida. Another example is more from the agriculture side, and that is crop classification. In the center image, you see that all those really bright colors. What we've done is actually segment out different agricultural fields to be able to identify which crops are growing. Is there wheat or soybeans or barley or something else? And then we can use that historical set of data to go back and train through time and see how those models performed in various seasons. You know, some years you might have a drought, other years we have tons of rain and flooding. So you need to be able to compare with known truths over time. And to give you just an idea, this is a tech conference, and we talk a lot about compute and scale and things like that, just to kind of quantify what type of scale some of these models run at. In 2015, we're just a few-month-old company, and we made our first agricultural models. And that was looking at the entire United States and our production of corn. And so to build those models, we processed around 4 quadrillion pixels of imagery. So that's hundreds of billions of iPhone photos. And we wanted to build a platform that we really optimized more for data scientist time. We wanted to promote rapid iterations of models. To get the accuracy we were looking for on that example, it took nearly 1,000 iterations in just a few weeks. So you can't get that rapid cadence of iterations on your models without being able to scale horizontally. And so our team uses our platform every day to continuously improve those products and improve the scaling. So hopefully that provides you an idea with a breadth of the types of ML models that we wanted to be able to run. That was kind of the goal of what we were trying to build. What does our workflow look like? Well, we start with a discovery phase. We investigate a hypothesis. We look at what types of data sets we have available, maybe what other data set we could bring in to help fuse together and provide insight. And then we build a lot of candidate models off those data sets. We create and evaluate those over historical or maybe a known truth. Maybe I knew where a location of a building was, or a radio tower or something like that. And then that model starts being evaluated and tested, and finally it goes into production. And then as we get new sensor data in all the time, just streaming, it's continuously updated, and it basically generates a continuous time series of analytics. So you can use our tools to make your own models, or our team of data scientists can actually build them on our behalf. And so at this point, I'd like to do a really quick demonstration. And it's a demonstration of typing my password. What we did was we took a big composite. This is aerial imagery of the entire US. This is all actually stored. We don't actually store any of this on PD disks. Haven't switched yet. Oh.
Are you good?
Oh, here we go. All right, try 2. So one interesting thing, none of this data is actually stored on PD disks. This is all being served straight off GCS. So that kind of gives you an idea of the speed of the Google network and GCS storage. But this is a huge map. This is tens of terabytes of imagery. So if you had to zoom in and look for objects inside of that, say, football fields, and I needed to look across terabytes and terabytes of imagery and find every single football field, that would take a huge amount of time. And so what we've done is we've gridded that huge composite image into tiny little grids, and then we've built a feature vector off each of those tiny little 128 by 128 pixel vectors, and then we've similarity search ranked them. And so what you're seeing is the most similar objects to the one I just selected. And so I could do this for anything. It could even be the railroad tracks right next to it, and it shows me all the most similar objects all across that entire composite. So that's a really quick example of the types of models we're trying to build. So at this point, just talking a little bit more about the GCP infrastructure that we use. We kind of have two main portions of our infrastructure that we have the ingestion, and that's very large bulk processing, and getting all of that data machine learning ready is kind of how we phrase it. And then there's our core APIs, and those are more of microservices based, and that's where we run all of our user workloads as well. So let's dive in to a little bit what we do. On those, to get that imagery ready, that's actually one of the biggest computational jobs we run as a company. We have to convert and georegister all of our imagery for accurate alignment. We have to convert it to standard projections. We need to do things like remove clouds and cloud shadows. These are really pesky problems that are kind of hard to deal with. We have to adjust for the camera angle of the sensor, the sun's angle, how that might affect what we're seeing back. We have to calibrate the sensors against themselves and their neighbors and compensate for degradations at the top of the atmosphere. So our goal is to take 20 years of camera technology, which things have changed a bit in 20 years, and to make those sensor outputs uniform and queryable and searchable all on the fly. This is a real example of what that looks like. On the left, you see a raw, completely uncalibrated, uncorrected imagery. Notice the calibration issues, the cloud cover, all of that. On the then as you move right, you can see the corrected versions. We also store vector data. An example of vector data would be maybe outlines of counties. It could be state outlines, city outlines, things like that. Another example might be statistics. In this example, it's actually the Panama Canal, if you didn't recognize that. And one thing you might have is some sort of a statistical data set. You might say how many ships pass through this portion of the image. So this is, from an architectural perspective, what those large bulk processing workloads look like on GCP. We source that data and bring that in, and then we use PubSub for breaking all of our work up into distributed asynchronous tasks. And PubSub, we found, has scaled tremendously. We can really hit it quite hard. And these asynchronous tasks actually fit really nicely into things like preemptible VMs, because each piece of work is very small in unit, and those machines can go away tomorrow, and we'll just keep spinning up new ones. So we love the cost savings that we can get when we leverage that. And one of the first examples of how we were actually gained a lot of confidence that we'd be able to do this type of workload on the cloud was scaling up and processing a petabyte of imagery. And we were able to scale that up to around a 30,000 CPU core job, and then run and process a petabyte of imagery in about 16 hours. And that gave us confidence, not just that we could get tons of cores, because we know we can do that almost anywhere. The bigger and harder problems actually are, would the object storage, would GCS be able to scale with that? Would the actual network, as we kept adding more and more nodes, would that be able to scale? And so we've actually seen close to high-performance supercomputing speeds on the GCS networks. And then we have these other data sets. They could be metadata or information about those raw pixels, or what we refer to as rasters. That could be informations about what bands of light, what modalities, what periods in time, things like that. We use all types of different persistent databases to store that. And then for error logging, tracing, things like that, we're not really in that business, so we're happy to try and use a no-op solution. So there we use things like stack drivers, tracing, erroring, and monitoring. So in terms of our core APIs, how do those microservices look? We have around approximately 50 microservices. Any given day, we have a new pre-alpha or alpha service coming up. We have canaries that we're trying out and things like that. So it's always in flux. But one of the core things that the reason we have microservices and we adapt them is we have so many different data types. It's actually really handy to be able to pair the persistent backend storage with for each microservice uniquely, and then be able to scale them individually. And Kubernetes multi-tenancy policies are generally set most of the time on a namespace basis. And we isolate various microservices by namespace, so then we can explicitly define policies, we can explicitly define how exactly we want to see it scale and react to load. We can do scaling interaction. We can control the interaction that goes through the control plane. So that's actually goes through our core APIs. And those core APIs become kind of the heartbeat of our system. Like, we really need to know and get as much visibility into that. Our end users, those workloads are also broke out into their own namespaces. Those workloads don't have any interaction with the backend Kubernetes control plane. For the most part, that's all going through our centralized API. And that's because on any given user, they might be able to scale jobs to 10,000 cores, and that's not that uncommon for us. So we need to really funnel that information almost as a proxy. So here's how at least I have thought about multi-tenancy on Kubernetes. This is an extremely broad subject. We could have a 3-day conference on it. And there's an amazing Kubernetes SIG working group that I'd highly recommend if you really want to dive super deep. They have calls every week. But for this, let's define multi-tenancy as a way to provide isolation for each tenant. That could be a user or an application. And on one extreme, that would be the far left. All of the users are actually in an enterprise. I know we don't trust all our coworkers, but let's say semi-trusted, I guess. And that's because maybe that organization has some sort of visibility into the process and standards and knowledge of the software that's going on those nodes. You're not just letting a regular user from the internet throw code up and start running in one of your namespaces. And often this paradigm can parallel a lot with what we see in kind of traditional IT, right? Where Kubernetes, you can have almost a namespace admin. That almost can kind of be the centralized IT function or how you're gatewaying in or out of workloads. And the far other extreme would be more of a platform as a service or a Kubernetes as a service. You have completely untrusted users running untrusted code, and they're having direct access straight into the Kubernetes API and control plane. You might need to do things like sandbox those workloads. You might need to isolate them on physical VMs or isolate them by various node pools. You could even need to look at something like gAdvisor or Kata containers to get that level of isolation. Our platform is more of a software as a service. So it's really kind of an in-between. The user interfaces directly with our core APIs. We don't actually give direct access to any of our Kubernetes control planes. And so those core APIs become that funnel or that proxy where all the traffic and the interaction with the cluster is coming. And so we need to allow a range of models to be executed. Those are all Python code on our API currently. And so we want to isolate each of those workers by their own namespace so we can execute them and then have them only interact with our APIs. So where does Istio come in? As those core APIs become that central proxy, we need to get as much visibility into that. That affects how the cluster is scaling. That affects how much money we spend, things like that that we really care about. So visibility becomes absolutely critical. And with distributed microservices, one of the biggest challenges is around the network. You've broken applications out, and they can run in many different locations. So getting visibility into where different services are running and that inter-service communication is absolutely important to get metrics and control. And I would imagine probably a lot of people, and there's references in some of the talks already, are familiar with Istio. It's an open source platform. Google and a number of others have contributed. It gives us load balancing for HTTP and gRPC traffic. You get fine-grained control of traffic and routing, retries, things like failover, fault injection, pluggable policies, automatic metrics, logs, traces, things like that. In a way, it kind of sounds a bit like magic. But in a practical way, it's actually quite a bit simpler. This is a diagram of the actual components there. And one of the keys of Istio is the Envoy proxy. Instead of adding client libraries and adding a client library for every single service, if I have a Node app, I need instrumentation libraries. If I have Python, I need that. If you even have something like we have Rust, maybe you need instrumentation libraries for all of those. That Envoy proxy instead gets deployed into your existing code. This could be a Python server, it could be a Tomcat server, it could be anything like that. And so all the traffic now goes through that proxy. And the proxy automatically talks back to the pilot component, and the pilot tells it where every single service is, where load balancing is, if there's any routing rules that are in effect. And then the mixer is where all of the telemetry and information starts to come in. That's where there's a pluggable logs layer where all your logs can get sucked up. It could go into something like Prometheus. In our case, we'll use things more like Stackdriver. And then finally, you have things like MTLS for service-to-service encryption. So if you're building a SaaS platform, there's some additional benefits to consider. Maybe you might be thinking about ingress or egress. You might say, I'll allow everything at star.googleapis.com to flow out into the world, but I'm not going to actually allow other sets of traffic. You can put that type of rule there. Maybe you would like to do, you're getting a lot of 500s, and for every 500, you think it might be a network blip. You might want to do automatic, I might want to retry it 3 times before I actually return back a 500. Maybe you'd like to do rate limiting. Your auth server might be hit 5 times a second. That might be great, but if it gets hit 50,000 times a second from one pod, well, I usually would call that a DDoS. So that type of thing is what we try and get out of Istio. So here's a diagram of what things look like afterwards, and overall, it's actually not that different. That's actually really awesome. You're not rewriting that code just to get that network reliability and that visibility between each of your services. We're now injecting the sidecar in with each of those workloads. Envoy reports all traffic telemetry straight up into the Istio mixer and provides visibility into each service, who's calling the service-to-service automations. Overall, we gain amazing insights into our core APIs that we actually did not have before. So with that, we would like to do a quick demonstration of some of the multi-tenancy workloads, and we will do a quick switch.
Cool. Okay, so I'm Sam Skillman. I head up the engineering team at Decart Labs. So as Tim was mentioning, we've got a lot of different workloads going on, from the simple to the very complex. So I'm going to show a bit of that right now. So if I go to this little simple application here, this is going to use our asynchronous task runner to essentially say hello world. what we do here is we define some function. It's going to end up posting a message to some webhook on Slack, which, if the internet keeps working, I'll start to see notifications on my desktop. I go ahead and create that function, give it a name, give it some Docker image that runs, how much memory it's going to need. This is kind of similar to like a cloud function-like functionality, serverless application. And I'm just going to run this. And I do that. And I can monitor what's going on through this interface here. So we see that there's 10 pending messages here. So as that goes out within Kubernetes, this is now finding appropriate resources to place those workloads, spin up those containers, and you can see we're starting to get Slack messages saying hello 1, hello 2. So that's all seeming to work. We can do something like we can attach a webhook to that task where I post a message saying like what's next. And eventually this would come in. We see that there's one pending message there. While that's running, we can look in here, look at logs for what happened to those messages. We do something like this. And that was the log from one of those, that Python function. This is just showing you the very basic functionalities there. I think, let's see. I think the hello next has not quite come in yet. But we don't make any money off of saying hello world. We spend most of our time running very large machine learning workloads at scale. To give you an idea of this, I had an idea, I guess it was probably like a few days ago, where you see some like really cool stuff like taking a Keras model that takes the style of one image and applies it to a set of other images. So I was like, okay, that would be pretty cool if we could pull this off during the demo. So we'll see if we can do it. So I essentially just copy and pasted this whole workflow here from Keras and modified it a bit so that what's going to happen is, let's see. I'm going to take Sentinel-2 imagery, which is from the European Space Agency. It revisits the same place on Earth every 5 days or so. Create a composite from that, and then run this large neural net transfer of one style to another. The details would take, again, much longer than we have left. So what I've done is I've already actually started running some of those while I was sitting in the chair right here. But what you can see happening on the back end is that this has taken taken our kind of internal namespace for each individual user and started scaling up the workload here. So if I get a new fresh look on here, this is climbing up. This is to 200 cores at the moment. This was down at, so this started at 107 about 6 minutes ago. And as the system responds to increased load, to more tasks running, needing to be run, it continues to scale that up in a way that doesn't just send a DDoS attack to our internal services. So it kind of gradually increases load over time. We'll come back to this in a second. Let's see. So a lot of these ones were quick ones, but then what this has done is then taken that Sentinel-2 imagery, downloaded it, extracted the style actually from Starry Night. It's like kind of the canonical version to take style from and apply it to elsewhere. It's then created a new data set in our system as part of our platform, sits next to the rest of our satellite imagery, other remotely sensed data, and started registering data to it. So this is this Sentinel-2 transfer live. It looks like we've gotten 6 scenes acquired so far. If I try to open this up, let's see if we can find it. It might take a little while, so the good thing is I've got some backup here. Where if you let this run for about another 10 minutes, you'll start to see the effects. So if we zoom out here, this is The United States, this is kind of California over here. It looks quite neat over in Africa. And so if we zoom in here, we can start to see the kind of swirly patterns that you get out of the Starry Night painting. And so this took something like 2,000 or 3,000 cores. It'll eventually scale up to maybe 20 minutes or so. And that's all running within my Kubernetes namespace that is dedicated just to my user so that this doesn't impact other users running on the system. We use all the auto-scaling abilities within Google Container Engine to just handle whatever increased load we have. Alongside of that, these are hitting our internal APIs at an increasingly high load when it's calling out to get those rasters of Sentinel-2 imagery. So those are also in turn scaling up as the load scales up itself. Last night, which was quite fun, I took a different data set, which was the National Agriculture Imagery Program does a high-resolution collection over the United States roughly every year. We might have to get there we go. So this is kind of the input data that went into this one. And if I look at what happens to that, we can zoom in here on AT&T Park. But this also took about 10 minutes or so, but scaling up to 1,000 or 2,000 vCPUs. Let's see how our workload is going here. We're starting to scale up, only 250, but that's not too bad. Yeah, so it's starting to process. Let's see if we can get lucky and find one that's just been live. There we go. So this was processed. We can take a look at it and say, take a look at this, and you can see that it was acquired. This is all UTC time, so 1:17 Pacific. So that's kind of one of the examples of meshing a whole lot of things together. Our internal data catalog that is, as Tim mentioned, over 10 petabytes of input data, all being able to run custom machine learning models, in this case using TensorFlow combined with Keras to do a fairly kind of useless from a business perspective, but interesting from a compute perspective application, all within the same system, but namespaced out, and being able to track that using all the kind of metrics that you can collect through Istio and all the other tools. So I think that's about it for that. You can see here, actually I can scale this up real quick so that you can see that this is just processing like 3,600 messages. There's a bunch that don't have any imagery, like over the ocean. This is currently up to 47 concurrent workers. Each of those workers have, I think, 16 cores. And so that's starting to be a real computation there. So that's it for that. Should I just transfer over to the?
Oh, yeah. Looks
Perfect.
like we already have our last slide. So with that, that's most of what we had to show. But some of you might be saying, hey, I have a use case. I don't want to go download petabytes and petabytes of data. I know how to build ML models. Well, for that, we actually have a platform that we offer, and you could get started right away if you have visibility into Python. Additionally, we have docs there and how to contact us and stuff. The earlier example I showed, search, is available at search at Decart Labs. You could look for other things besides railroads and baseball fields or football fields. And then finally, if any of you are interested in working on this type of stuff, we're always looking for more brilliant people. So with that, I'd like to thank you.